Okay, so this is our final video in our Year 10 Polynomials topic. And what we're looking at here is how we go about finding the equation of a polynomial graph. So throughout the topic, we've built up the algebraic tools that we needed in order to be able to factorize and then hence solve cubic equations. That was important in order to enable us to sketch cubic graphs so that we could find the intercepts. And now that we know how to sketch cubic graphs from their equation, we want to be able to think about reversing that process. So if we're given the graph or information about the graph, can we get back to the equation? Okay, so let's just work through some examples here. So the first example here, we clearly have a cubic with a point of inflection. Now we know that graphs of this shape, their equations take this form. Okay, so that's the form we're going to start with. We know that the point of inflection corresponds with hk. Okay, so we know that this is y equals a times x minus 1 cubed. It's translated to the right by 1 and up by 5, so plus 5. So we know that. And then we just need to calculate a. So as I've said before when we've done this with the parabolas, if you've got a cubic with its point of inflection at this point, that doesn't tell you how steep it might be, which way it goes, etc. So what we need now is to work out, to use information that tells us, allows us to come up with an equation that is exactly this particular cubic with the point of inflection at 1, 5. So we're going to need to use that point 0,3. So we sub 0,3 into the equation, which means when x equals 0, y equals 3. Okay, so I'm going to subtract 5, so that's negative 2. And then this is a times negative 1 cubed. Now remember, when we cube a negative, it's still going to be negative. So it's a times negative 1, and then a is going to be negative 2 divided by negative 1, and so therefore it's positive 2. So therefore our equation is 2 times x minus 1 cubed. Again, don't forget, the places you'll make mistakes here are just careless. You'll have done all the hard work and you'll leave a cubed off, or you'll accidentally write it as a squared, which means it's certainly not the equation for this graph. So just take a bit of care. And then plus 5. So that's our equation. Okay, let's have a look at another one. Find the equation of the graph pictured. Okay, so this looks like it's a quartic shape, and we know when we have this flat-bottomed quartic shape that it's because it is a quartic equation, of this form. Okay, so once again, the turning point tells us about hk. So straight away we know that y is equal to a times x minus 3. It's gone to the right by 3, power of 4, and up 4. Okay. Again, don't lose your power of 4. That will be a mistake you'll make somewhere along the way. And once again, just like the previous example, just knowing about the turning point alone doesn't tell us whether it's a very sort of thin, squashed quartic, whether it's a wide, fat one, doesn't tell us which way up it goes. So we need to be using some other information, which in this case is going to be that point. It won't always be the y-intercept, but in this case you essentially need another point somewhere that we're going to sub in to find what a has to be. Now, I know in this particular example that I'm expecting a to be negative. I can tell that because I can tell that it's an upside down quartic. Okay, what I would really discourage you from doing, a number of students like to, tend to sort of write negative a here. I find if you do that, you get yourself confused at the end. You end up with a positive number, and then I think it's easier just to calculate a, knowing that in this instance you expect that you will get a equals something negative. Okay. Alright, so let's substitute the point 0, negative 5. So that is when x equals 0, y equals negative 5. Okay, I'm going to take away 4, so that's negative 9. And then we've got a times, now negative 3 to the power of 4. So a negative number to an even power is going to become positive. So it's just the same as 3 to the power of 4. And 3 to the power of 4 is 81. And so a is going to be negative 9 on 81, which is negative 1 on 9. And so therefore the equation is going to be negative 1/9 x minus 3 to the power of 4 plus 4. And there's our equation. Okay, let's have a look at the third example. So clearly it's a cubic. Okay, we've got 3x intercepts here. It's not a cubic of, this form or this form, so it's not going to be an equation of this form. Okay, it's not going to take that form. And so what we want to instead use here is we want to use the 3x intercepts to start us off with the factorized form. Okay, so we know that if there's an x-intercept at 0, then x will be a factor. Okay, we know if there's an x-intercept at 2, x minus 2 will be a factor. And we know if there's an x-intercept at 6, x minus 6 will be a factor. So we know in its factorized form that's what it's going to look like. The one thing we don't know is any possible stretch or dilation that might be happening. So once again, we can draw infinitely many different cubics that have these 3 x-intercepts. They can go this way instead, okay? So what we want to know is the particular cubic that has these 3 x-intercepts, and therefore we've got another point here that we're going to use to enable us to find the particular dilation factor. Again, like the previous example, what I do know is because it's a cubic that goes down as it goes from left to right, I know that a is going to be less than 0. Okay, so I expect that when I find my answer, I know a is going to be a negative number. Okay, so let's substitute the point 4, 8. So that is when x equals 4, y equals 8. So it's a times 4 minus 2, which is 2, times 4 minus 6, which is negative 2. So it's 8 equals a times negative 16. And so a is 8 on negative 16, which is negative 1/2. So negative, good, that marries with what I know. And so therefore my equation is negative 1/2 x times x minus 2 times x minus 6. There's no reason to expand that out. That's the equation of the graph. Okay, let's have a look at the fourth and final example. So this time we've got 3 turning points, so it looks like it's a quartic function. Okay, again, it's not a quartic of this shape, and so it's not going to be an equation of this form. Okay, so we know it's not that. So we're going to instead use our information about our x-intercepts to find the equation. Now, the important thing to note here is that there's a turning point at this x-intercept, and so this will be a squared factor, this one. Okay, so in terms of listing out our x-intercepts, so we've got an x-intercept at negative 5, which means we'll have a factor of x plus 5, and because it's a turning point at that point, it'll be x plus 5 squared. There's an x-intercept at 1, which means there'll be a factor of x minus 1, and there's an x-intercept at 2, which means there'll be a factor at x minus 2. Once again, we need to think about the dilation, okay? And that's where we're going to use our additional point, which in this case is a y-intercept at 0, 50, okay? So we're going to substitute the point 0, 50, and so we're going to get, when x equals 0, y equals 50, so 50 equals a times 5 squared times negative 1 times negative 2. Okay, so that's 50 equals a times 25 times negative 1 times negative 2 is positive 2. So it's 50 equals 50a, and so a indeed in this case equals 1, and so therefore our equation is just x plus 5 squared times x minus 1 times x minus 2. I just want to caution you that if you just went straight from the graph to this equation, you wouldn't earn full marks for that because there's no evidence that you've actually thought about the fact that it might be dilated. Yes, in this case, by the time we calculated a is just 1, so there is no dilation, and so in fact, if we'd ignored a back here, we would have had the right equation, but we would have just had the right equation by accident, not because we actually knew it was the right equation. Okay, so making sure that you always consider the possible dilation factor, use a point to calculate that value. If it happens to be 1, fine, but you need to know that, not just assume that. Okay. All right, so the work today is from a worksheet finding the equation of a polynomial graph.